Yeah, I'm Carl Wellington, as you mentioned, Director of Autonomy at Aurora, and today I'll be talking about bridging perception to motion planning. So at Aurora, we're building the Aurora Driver, and our first product will be trucking. So trucking is a really great application for autonomy because we can split the problem into two parts by establishing hubs in major cities. And this allows human drivers to perform the complex city driving, as well as also stay close to home. And then allows us to focus on the long haul, the repetitive highway driving from hub to hub. And so today it takes almost 3 days for a truck to deliver goods from Dallas to Los Angeles, given the breaks that human drivers need. And we can bring this down to 24 hours. So there's a real benefit here. We're also pursuing ride hailing to bring the benefits of self-driving to cities and to people who want to get where they want to get. And there's strong overlap between these two use cases because a lot of the most important ride-hailing trips are actually also involve a lot of highway driving. So we're really just building one Aurora Driver to kind of support both of these two use cases. All right, so how does the system look? Well, it's like other self-driving systems. We have a perception system that takes sensor data and builds a representation. We have a motion planner that uses that representation to make decisions. And there's a lot of interesting work, including things we've already seen today. It's been already a great workshop, and I'm excited to see the things coming this afternoon on how to bring these things together. So given the speeds involved in driving, knowing just the locations of the actors is not enough. We need to know where they're going. So with that in mind, a common approach is to use actor forecasting. And so in this talk, I'm going to be talking about forecasting and some different ways to think about it within the system, and kind of both from sort of a left to right perspective, as well as then a right to left. So let's start left to right. One really interesting area is to view the kind of perception forecasting problem jointly as a single problem. And this is based on the pioneering work of Raquel Urtasun in her lab. And they showed that by learning a joint perception forecasting model, we can both simplify the system and then also get more accurate forecasts. So I'd like to talk a little bit about some of the work that we've done in this area. Okay, so what does this look like? Here's kind of a typical setup. You've got a sequence of LiDAR sweeps coming in. You've got a map. You extract features from both of these. You bring them together and combine them to produce both detections and forecasts. And so you train this end to end. For the detection, you may use a standard focal loss. For forecasts, we could use a L1 regression loss on both the box size as well as its centers and orientations going forward to kind of get the forecasts, and then train this jointly end to end to get both detections and forecasts. So one of the areas that we've been looking at in this space is really thinking about how do we think about these forecasts in terms of multimodality and also thinking about uncertainty. So here's an actor highlighted. And if you look at this actor, we don't yet know where this actor is going to go, right? It may go straight, may make a turn. If we have a single mode forecasting system, kind of as shown on the left, then it's probably reasonable to produce just a go straight trajectory. But of course, we don't actually know. So we'd like to think about having multiple modes and then put probabilities on those in kind of a discrete probability sense. More than having the discrete probability, we also want to think about having a distribution over the actual motions that the vehicle might take for each of those. And so this is shown on the right. We kind of have these multimodal forecasts with both the sort of discrete probabilities on the modes as well as the continuous uncertainty distributions for the actual trajectories. And this is really important because if you're giving these forecasts to a motion planning system, being able to understand how certain you are with them about what the other actor is going to do, as well as about how they're going to actually move through space, is really important to be able to make good decisions. So how do we do this? Well, we can assume a Laplacian distribution over basically the long track and cross track errors of these forecasts. And so then instead of optimizing kind of an L1 loss, as we talked about before on the box centers, we can minimize the KL divergence between these along track and cross track errors with the distributions. And if we look at this and actually kind of look at the actual error distributions that these models produce, you can see that they're well calibrated. This means that we can actually trust these distributions. This is a good result because then the uncertainties that are being produced can be used by the motion planner to make good decisions. Okay, another thing that is important is this. If we're thinking about trying to predict the future, we really want to make good velocity estimates. And of course, using a sequence of LiDAR data over time is part of this, but we want to bring in other sensor data as well. And so here we show bringing in basically radar information. And we can do the same thing, bring in radar information, do another feature extraction, bring it in, and do the same kind of end-to-end learning to make sure that the features that we're learning from each of these sensor modalities are actually supporting the core outputs of detection and forecasting. So here's some work we've presented last year, and just a couple examples of kind of some of the benefits that you get from bringing radar in. Here you see on the top, there's the highlighted actor, and based on just the bit of motion we've seen from the LiDAR data, there's still kind of these multiple modes of what the vehicle might be doing going forward. With the addition of the better velocity, direct velocity measurements from the radar, this actually induces an interesting mode collapse here, where it actually becomes much more certain that the vehicle is just pulling out and going forward, and then we can make the right decision based on that. Here's another example. It's a little hard to see here, but basically this actor highlighted on the left has just come out of occlusion. So this is sort of the first time you get LiDAR data on this actor. And so we get a detection right away, but on the left, we've only seen it once, so we really don't know what the forward motion is or velocities. Whereas, again, the nice thing about getting instantaneous radar velocities on this is that we can get accurate forecast of its future motion right away as soon as that actor comes out of occlusion. And of course, this is really important for actors that maybe kind of quick reveal cases to be able to get a motion as quickly as possible. All right. Another area that is related to this is to think about input representation. And this is something that our team spent a lot of time thinking about, because a lot of the approaches out there really start with kind of 3D LiDAR points as the first thing you start with. But of course, this is not what's actually happening, right? We don't have a drone that's flying up above us getting bird's eye LiDAR points that then we can start processing. The actual LiDAR data we get comes from basically a range sensor. We're getting range measurements, and we can choose to project those in the 3D world if we want. But it's the actual data we're receiving is this range information. Then, of course, you get this over time. So you have basically a sequence of range views. And you can kind of see how things move and change in terms of shape and size as things move through the world. Just as before, right, we want the same output. We want basically to have essentially a bird's eye output of detections as well as forecasts with uncertainties, just like before. But now we'd like to think about, well, could we use this raw input data and take this directly? And this is interesting because, of course, we've seen with a lot of end-to-end deep learning approaches in general that they can often perform better if you actually give it the raw data directly instead of kind of pre-processing certain things. So the range view has a number of benefits, right? One thing is it does avoid approximations that we often use, like voxelization or other ways of kind of putting the 3D data and getting it a little bit easier to process, because it actually processes every single LiDAR point. This is especially beneficial for pedestrians or other kind of small objects. There's also a lot of structure because the range view encapsulates how the data was actually captured. And so you get the relationships between, for example, which objects are including which other objects or other scene structure that can be lost when you take this data and project it in a 3D view, especially if there's something including something much further away from it. And of course, as you see on the left, this is a really nice, dense input representation that is well suited to efficient convolutions and being kind of computationally efficient compared to kind of the sparse representation that we see on the right. Of course, there's also challenges, right? There's no consistent world frame in the range view. Everything is changing. It's like using images, right? Where objects not only are just moving around, but they're actually changing size, they're changing shape. And so a lot of our work, and references below, has focused on basically building network structures that encode the structure of the problem into the network and basically extracting features in each of these, the range view directly, but then warping views together to be able to combine these things temporally. And this gets really important when we think about long ranges, right? And so here we see that, on the right is a typical LiDAR sensor you get today. where you might have a 200-meter range. And so this is kind of looking at over a 400-meter by 400-meter square. And so the nice thing about operating the range view is that because you're doing a lot of the processing on the input space, which doesn't change based on range, you're almost, your computer is almost independent of the kind of range you want to do. And so this is really great when you want to do really big ranges like on the right, or of course, Aurora has an internal LiDAR, which we call First Light, which has much longer ranges still, which is important for high-speed driving. And kind of operating in the range view supports these really high long distance ranges because it stays dense instead of the sparse representation as you see on the right. All right. One more advantage of thinking about things in the range view is it is very natural to combine with other range view sensors, such as cameras. And so here you see, again, an example where you have the range view, which we can extract the LiDAR features. We have a camera image, which we can also extract and do feature extraction directly in the camera view. Take those camera features, basically project them into the LiDAR points, and then send these along in just the same way. And so it's a very natural and easy way to kind of combine these two different types of sensor data. We can also put these together with the whole system, right? We have the existing approach that I've talked about up above, and now we can bring in these new range view, both in the LiDAR as well as the camera, do feature extraction in the native view of those sensors, do a projection into the bird's eye, and then combine these things again into one kind of unified model that brings all of these things together. And if you look at, again, there's some work reference there, but if you look at a few examples, you can see some highlighted actors here, and it really helps in areas that are kind of small or occluded regions. These are these areas that I think having the sort of direct range view or camera information helps, like this occluded vehicle gets a better detection, or in this middle case where the kind of our baseline only detects one of these two pedestrians, but there's actually two, or this small actor over on the right. And as we take this forward even more, we start thinking about sequences of both sequences in the range view as well as sequences in the bird's eye view, and how to put all of these together. And if you're interested in this, please attend the afternoon poster session where we have work being presented on this directly. And it's just a nice piece of work, so please check that out in this afternoon's poster session. Okay, so what does this look like overall? Here's a kind of typical urban setting. You kind of see how it all comes together. You get a bunch of different actors, you get these predictions for pedestrians, vehicles, bicycles, and these are then able to be brought into Motion Planner to be able to make good decisions. Okay, so now if we step back, what have we learned? First of all, learning forecasts end-to-end with these kind of multimodal output distributions and calibrated uncertainties. I think this we've shown some really strong results in some various papers referenced earlier in this. And also we've talked about the benefits of multiple views and multiple different sensing modalities. I think one really key point to take out of this part is that the features that you want on the sensors, on the sensor data, for understanding the motion of actors in velocities and these things are often quite different than the features that you want for detection. And so by training end-to-end, we improve our performance not just on the forecasts, but also on actor state information like velocity. And this is, I think, one of the really key points that I'll kind of come back to later. Okay, so this is great. We have this joint model, and we can pass in the decision maker. Of course, there's some problems with this. Here's a typical scene that we see all the time on the highway. And we're driving down the highway. We've got people merging in from the right. And we need to make a decision. We need to either hold our lane and kind of let the next actor kind of slide in behind us, or maybe we slow down and let that actor go in front of us. So we have this joint interaction, right? Where we need to make a decision. And of course, this other actor is observing what we're doing and then is making decisions based on that. And we have this kind of interesting joint interaction. Of course, all of us who've done highway merges know this can be quite complex sometimes. So let's think about applying the forecasting approach that we just discussed to this problem, right? We go out, we collect a bunch of data of good interactions by expert human drivers, and then we start letting the model learn, right? And the model is going to see that sometimes this actor to our right goes in front of us, kind of accelerates, sometimes the actor to our right slows down. And so we have kind of this multimodal distribution there. Well, this is fine, right? We just talked about how these models actually handle multimodal distributions, handle uncertainty. They handle these quite well. So we can generate this and actually generate this multimodal forecast. But then what happens when this gets presented to the motion planner, right? And so if we kind of click this, we can play this forward and think about, well, we're going to generate these two kind of possible actions, right, that we've seen based on our data, these two forecasts, right? One that the actor slows down, one that it speeds up. So the challenge with this, of course, is that then when the motion planner looks at this, we kind of put the motion planner in a tough spot because when holding our lane doesn't look good because there's a good chance that this other actor is going to be there at the same time. Slowing down doesn't look good either because there's also a good chance from the forecast that the actor will be there. And so then one option it might take is actually to just hit the brakes hard and kind of protect against either of these things happening. And this is really unfortunate because actually either of those first options would have worked out well. And now it actually does something quite different because it doesn't have the right information to be able to make this decision. So of course, this is the well-known problem of just providing a marginal. And there's great work out looking at kind of actor interactions or graph structures, and even some work earlier today on this about how to kind of produce self-consistent forecasts. But the thing to remember here is that the AV is not a passive actor. It's not a passive observer here of the situation, trying to figure out what's going to happen, right? The real issue is that the data that was collected for these forecasts is all conditioned on what the other actor is doing when that data was collected, right? That's how that person made the decision about whether to accelerate or slow down, is conditioned on this. So why don't we embrace this, right? Why don't we just embrace this and shift things around and take this forecasting and say, okay, we're going to make these forecasts conditioned on the decisions of the AV. And so we can now split this apart into two cases. So in the top, right, the AV basically says, okay, we're going to slow down, let this actor in. In the bottom, we're going to hold our lane and let them slot in behind. And then based on those actions, we can again go and do our forecasting and see that actually both of these options result in good outcomes. And so by basically shifting the forecasting around from being kind of this forward pass to a conditional forecast based on our decisions, we can get the good outcome. And of course, you see this in practice, where here there's kind of a slot that looks a little too small for us initially, but then because we can condition and say, okay, if we establish our place here, we can forecast conditionally this other actor is going to move back, give us space, and slot in well. This isn't just for merging, of course, other things too. Here's a lane change. We have to move over due to construction. Again, and not enough space initially, but we can signal our intent with our turn signal and then reason about the fact that by doing that, we expect this other actor to move back, give us space, which allows us to successfully move over. Okay, so we've talked about forecasting a bit, but there is this broader thing about decisions. And although I won't talk deeply in here, I think we have to acknowledge that making these decisions is complex. And Aurora's approach here has been to learn these decisions from human driving data, right? And that one of the things that's really important about how to think about this is that driving in a predictable human-like way is very important for safe driving. So here we show some cut-ins, finding an interesting slot. And on the bottom right, a case where we actually take these, learned models and then wrap them in a kind of verified safety guardrail so that in this case, when the light turns green, we start to go, there's a red light runner, we can still react appropriately. Okay, so now we've shown that the benefits and how important it is to kind of do the conditional forecasting within the motion planner. Okay, well, now what do we do, right? We've talked about the benefits of forecasting as part of perception. We've also talked about how important it is to do this part of decision-making. And this is, of course, the great interesting thing about this problem, right? And we've already seen some really interesting approaches earlier today. I expect we'll see more this afternoon. And there's sort of a ton of interesting work in this area of how to think about bringing all these things together. So one way we've been looking at is to focus on actor goals. And just to set up this problem, we have a case here where, again, typical case driving down the highway. We're just driving right along, following behind this pickup truck. And if I just move it forward one step, we see that basically the actor motions haven't really changed. Everyone's continuing to do just what they did before. But now there's a few extra pixels in this image lit up, which is showing that this white car now has their turn signal on. And this, of course, changes everything, right? Because now we know that this actor wants to get over. We don't know when, we don't know exactly how. Maybe they're just moving over when it's convenient. Maybe this is their exit and they're going to move over right away. But we can, again, start making these decisions and start doing this conditional forecasting interactions based on this actor because we know where it's trying to go. And as we try to formulate this kind of goal problem, here's another work we presented last year, thinking about goals relative to map geometry. And so here you think about that we have maps, and so the vehicles tend to follow the lanes in the map. Even pedestrians, right, are either generally following pedestrian areas or perhaps trying to get from one pedestrian area, like one sidewalk, to another sidewalk. And so there's a way to kind of reason pretty directly from the map geometry and kind of propose this problem in the context of the map geometry and get a natural generalization to new scenes, even if it's a complicated geometry that we've never seen before. If we look at what this looks like in practice, here's a couple examples of kind of ground truth of what actually happens, and then this goals being generated. And you see on the left case, lots of different options, and lots of different options are open, right? And so we kind of really generate this multimodal distribution over these different possibilities. The second option here is a little different because given the velocity of the vehicle, it's extremely unlikely this vehicle is now making a right. So we can actually use the motion of the actor to know that the goal is to go forward and reason about that. And of course, whenever using a map-based approach, you always want to have a fallback that says, look, if this actor doesn't match any of these goals, there's probably a different goal this has that isn't represented by the map, and being able to highlight that one if it doesn't match what the map says. Okay, so that's kind of in the vehicle side. Then there's this really interesting case that's, of course, so important in self-driving when you're looking at a pedestrian and trying to figure out whether they're going to cross or not. So at the top bar here, this t equals 0 space, here's an actor that's on the side of the road with no velocity. So if you give this and need to make a decision from motion planning side, just based on the state, here's an actor on the sidewalk with no velocity. It's pretty hard to know that this actor is someone that's going to interact with us and that we need to start reasoning in that way about. So here we show some results of a model that's basically trained directly on sensor data to predict these crossing goals, and it's combined with the geometrical reasoning we just from the map that we talked about just earlier. And so using these visual features, as you can see here, there are these indications that this actor is about to move even though they haven't really started moving yet. And so you can see in the top row that there's this red part about that there is a starting to get a crossing goal, even though the person hasn't moved yet. Of course, we don't know exactly how they're going to cross or when they're going to cross, but we know that they can start reasoning about this, start having these interactions, start doing this conditional reasoning. And then, of course, as the actor continues to move, the probabilities move around and show even a more certainty around the fact that this is their goal to cross. So one thing that's important here too is that there's lots of different ways to possibly recognize about gaze or other aspects of this, but the really important thing is whether they're going to try to cross or not. So you can think about this goal almost like the turn signal state up ahead, where it's like signaling a goal, signaling intent, and having to learn this directly from sensor data in kind of an end-to-end way. Okay, so where did we end up? As I mentioned earlier, there's lots of different ways to think about this problem, and that's what makes this so interesting. One way that we can kind of put together a couple of the different themes that I've been talking about today is to think about there being a forward reasoning pass. And this can really benefit from a lot of the advantages that we talked about in the first part, right? So this is generating actors and actor goals and trying to really use this end-to-end training from temporal sensor sequences all the way into the future, gaining the benefits of better state estimates from doing that, as well as learned uncertainties, but then bringing in this idea of these goals and understanding where are these actors trying to get. The key thing here then, the difference, is to not, at this point, try to forecast the exact spatiotemporal path, right? We know that this actor is trying to cross. We know this actor is trying to get over. We don't know exactly how or when they're going to do that. That part's going to be done over on the conditional, on this part on the right, where we can do conditional forecasting based on our decisions, potential decisions, and look at that jointly, because that really depends, the actual end up motion of this actor really depends on our own actions. So we have this kind of forward reasoning pass that's have stuff that's independent of the AV. And then we have this interleaved reasoning part that reasons about other actors in the context of the AV's decisions. So of course, one thing you might ask is, well, wait, why split here at all, right? Why have any split? Why don't we just do these end to end? And I do think that there are really compelling reasons to think about doing end-to-end training, right? All the same reasons about reasoning about the future has better kind of sensor feature extraction. Thinking about what's actually needed all the way to the end is really important here too. And there was some great work on this earlier today. One reason you may want to be thinking this way is at Aurora, we think a lot about verification. And when we're doing verification, we want to test against cases that we've seen, and of course, many cases that we've never seen. And so you could build a full sensor simulator and simulate everything kind of from the raw data. And we do this, but the parts on the left here in that forward reasoning stage are often the really computationally expensive part. So if you think about kind of having a fixed budget for your cloud spend, it can be more effective to think about, yep, doing some simulations directly from log or sensor simulations, but then doing a huge number on this interleaved reasoning part, on the motion planning, on the conditional forecasting part, where you're able to put in the parts of the problem that are not dependent on the AV and really focus on these complicated interactions. And so this is one way that we've been kind of going about thinking about this problem, both for terms of how you set it up, as well as how you verify it. With that, I'll stop and just mention again, it's so interesting to be in this space and see all the different stuff. I've been already learning a lot of things from this morning, and can't wait till the sessions this afternoon.